Welcome to all. In this lecture session, we will see the cycloconverters and some of its configurations. So here the basic block diagram of cycloconverter is shown here. So cycloconverter basically converts input power at one frequency to output power at different frequency. It is basically a frequency converter. So whenever the application requires variable frequency with the available source with fixed frequency, cycloconverters will be used for those applications. So when it comes to the classification, we can classify cycloconverters based upon two factors. The first factor based upon the output frequency. So this is the first classification of cycloconverter. So this is based on output frequency level. If the output frequency is less than source frequency, we can call it as step-down cyclo converter. And on the other hand, if the output frequency is greater than source frequency, we can call it as step-up cyclo converter. So similar to your step-down transformer and step-up transformer, their voltage level is changing, here frequency level is changing. So step-up cyclo converter and step-down cyclo converter. Now cycloconverters are also classified based upon circuit configuration, similar to our rectifiers, midpoint rectifiers and bridge rectifiers. Here we are having midpoint cycloconverters and bridge type cycloconverter. So we are having the combinations: midpoint step down cycloconverter, midpoint step up cycloconverter, bridge type step down cycloconverter, bridge type step up cycloconverter. So these are the various possibilities of cycloconverters we are going to have. So when it comes to the applications, so by changing the frequency, we know we can change the speed of the AC drive. So variable operation of AC drives. So that is one application. Another one is static wear compensation, that is reactive power compensation. And another major application is aircraft or shipboard applications. In aircraft and shipboards, different components require different frequency levels, so that in those cases cycloconverters will be used. So the next topic is midpoint cycloconverter with R load. As I already told in the introduction, we are having midpoint step down cycloconverter, midpoint step up cycloconverter, bridge type step down cycloconverter, and bridge type step up cycloconverter. So the first possibility we will see midpoint step down cycloconverter with R load. So as we know, cycloconverter converts one frequency level to the another frequency level. So here in this circuit diagram, so this is the midpoint cyclo converter with R load. So this is the power circuit of that particular thing. So if you observe here, a source Vs is connected at the input side, a midpoint transformer is placed, then two anti-parallel sets of thyristors. So total 4 thyristors are placed in a structured manner. Then your load is a resistive load. So load is connected between midpoint of the transformer and common connection of your anti-parallel connected SCRs. So this is the structured connection of cyclo converter to form a midpoint cyclo converter. So if you see, we are having different names for 4 thyristors: P1, N1, P2 and 2. So if you understand these namings of these thyristors, the understanding of principle of operation becomes very easy. We'll try to analyze those things now. Let us assume I'm having a source voltage Vs here. So that is given to the primary of the transformer. Now at the secondary of the transformer, two windings are there. So one winding voltage is VA0, another winding voltage is VB0. So B is the terminal here and A is the terminal here and O is the mid terminal of your midpoint transformer. So first for this source voltage, positive half cycle and negative half cycle, I am considering one full cycle. We will try to draw the VA naught and VB naught. So here we'll take VA naught on this color and VB naught with this color, VB naught. So VA naught and VS both will be in phase. So pi to pi. What about VB naught? It is 180-degree phase shift with respect to Vs. So this is my Vs now, and Va naught and Vb naught. Alright, now first I'll write positive half cycle of Vs. So Va naught is having positive half cycle. Vb naught is having negative half cycle. Right or wrong? Alright, so 0 to pi. This is 0 to pi. Now 0 to pi, if you see here, A terminal is positive with respect to A, O is negative. B terminal is negative with respect to B, O is positive, because VB naught is having negative half cycle from 0 to pi. So during this period, this plus is applying it. So we'll see from 0 to pi. So plus is applying it P1 anode. So P1 will be in forward blocking mode, and this minus is applying it N2 cathode. From the bottom part, N2 will be in forward blocking mode. So 0 to pi, this portion is completed from the source side. So simply I will say, when source cycle is positive half cycle, then P1 will be in forward blocking mode, N2 will be in forward blocking mode. Now pi to 2 pi. So pi to 2 pi. So at pi, both the polarities are getting reversed. Now A becomes negative with respect to A, O becomes positive, and B becomes positive with respect to B, O becomes negative. So this minus is applying it N1 cathode. So during this period, pi to 2 pi of the source voltage, N1 will be in forward blocking mode, and from here this plus is applied to P2 anode. So P2 will be in forward blocking mode. So simply this is my conclusion. During positive half cycle of the supply, P1 from the top group and N2 from the bottom group will be in forward blocking mode. So P1 and N2 will be in forward blocking mode. During negative half cycle of the source voltage, N1 and P2 will be in forward blocking mode. So this is one conclusion. And coming to the other point, why we have given these names as P1, P2 and N1, N2. So P1, P2 are positive group switches. N1 and 2 are negative group switches. Why I am calling them as positive group and negative group? So positive group switches means when positive group switch is in conduction, the output voltage is expected as positive. When negative group switches are in conduction, the output voltage is expected as negative half cycle. Simply, when P1 is in conduction, P-type switches are in conduction, then I can say the output voltage is having positive half cycle. When N group switches and N1 or N2 are in conduction, I can expect negative half cycle in the output voltage. We will see why. So we will see that if you observe the directions of the current, easily we can say that. So when P1 is in conduction, the current flow starts at A, P1 to resistor right side to O. So the current is entering from this side. So let us assume this is your reference terminal. So whenever current is entering this side, we can say that output voltage polarity will be positive. We can expect positive half cycle. So when P1 is in conduction, the current is entering from this side, so that is the positive half cycle. Now see, we'll see when P2 is in conduction. So when P2 is in conduction, it starts from B to P2 to load right side to O. Again it is entering from the right side of the load terminal, so we can say positive half cycle in the output. So now we'll see when N1 and N2 are in conduction. When N1 and N2 are in conduction, the current flow starts from, let us say when N1 is in conduction, so the current flow starts from O to left side of the resistor, and then N1 to A. So this is the current flow. That means the current is entering from the left terminal of the resistor, so that the output voltage polarity will be negative. Similarly, when T2 is in conduction, N2 is in conduction, so it starts from O to left terminal of resistor, then N2 to B. Again it is entering from the left terminal, so that the output voltage polarity will be negative. So if you understand these 2 points, the analysis of cycloconverter is over. The first point is simple. So during positive half cycle of the source voltage, P1 and N2 will be in forward blocking mode. During negative half cycle of the supply voltage, N1 and P2 will be in forward blocking mode. We can give triggering pulses for these switches. Alright. Similarly, when P1 and P2 are in conduction, the output voltage and current are positive half cycles. When N1 and N2 are in conduction, the output voltage is having negative half cycles. So don't be confused with these points. So one is related to forward blocking mode and another one is related to output voltage polarity. Alright, so based upon this information, we'll try to draw the waveforms for this. Again, I'm writing those points here. During positive half cycle of the switches, so positive half cycle of source voltage, cycle of Vs, we are going to have P1 comma N2 are in forward blocking mode. During negative half cycle of the supply voltage, P2 N1 are in forward blocking mode. So P1 P2 are in conduction, positive half cycle at output. N1 and 2 are in conduction, negative half cycle at output. So if I am having these points, the analysis of cycloconverter becomes pretty easy. Now, alright, so let us assume my requirement is output frequency is 1/3 of supply frequency. That means whenever the supply frequency completes 3 cycles, output voltage has to complete 1 cycle. So that is the meaning of this statement. The output frequency should be 1/3 of supply frequency. So for better understanding, each half cycle of the source voltage given is the number 1, 2, 3, 4, 5, 6, 7. Right. During the first half cycle of the source voltage, that is positive half cycle. So what is our target? When source voltage completes 3 cycles, the output voltage has to complete 1 cycle. That is your target. That means these 3 half cycles should be converted into positive half cycles. These 3 half cycles, 4, 5, 6 half cycles should be converted into negative half cycles in the output. Alright, so for that our usual practice, indicate zero crossings and indicate triggering instants. So here zero crossings are indicated with red lines and triggering instants are indicated with green lines. Let us assume during the first half cycle, that is the positive half cycle of the source voltage. During the positive half cycle of the source voltage, what are the switches will be in forward blocking mode? P1 and N2. What is the required output voltage here? Positive half cycle. So 0 to alpha, voltage and current will be 0. At alpha, I require positive half cycle, so that I will give triggering pulse to P1, because P1 and N2 are in forward blocking mode during positive half cycle of the supply. At pi, it goes to off state. Natural commutation occurs in this case of step-down cyclo converters. Pi to pi plus alpha, no switch will be in conduction. Now in the source I am having negative half cycle, but I require positive half cycle in the output. So during negative half cycle of the supply voltage, P2 and N1 are in forward blocking, but I require positive half cycle. So triggering pulse has to give in to P2, so that I'll get positive half cycle. Now at 2 pi, P2 goes to off state as reverse voltage applied and current drops below the holding current for P2. Now 2 pi to 2 pi plus alpha, no switch will be in conduction. Now again positive half cycle of the source voltage, P1 and N2 will be in forward blocking mode. As my requirement is positive half cycle, triggering pulse will be given to P1. So first three half cycles of the source voltage have converted them into positive half cycles in the output. Now next three half cycles I need to convert it into negative half cycles, as at 3 pi P1 is naturally commutated 3 pi to 3 pi plus alpha, no switch will be in conduction. So here source voltage is negative half cycle. During negative half cycle, what are the switches will be in forward blocking mode? P to N1, so that I want negative half cycle in the output, triggering pulse will be given to N1. So at 4 pi, N1 goes to off state. Again positive half cycle of the supply voltage here. So during positive half cycle of the supply voltage, P1 and N2 are in forward blocking mode, as my requirement is negative half cycle, triggering pulse will be given to N2. Again here the triggering pulse will be given to N1. So if you carefully observe, so 3 cycles are completed here in the source, but here if you draw the moving average of this, only one cycle is completed. Draw the moving average, only one cycle is completed. So this is my requirement. So the output frequency is 1/3 of supply frequency. So the output frequency is less than supply frequency. So one cycle is completed. Again next cycle starts here at the for the 7 positive half cycle. Again my requirement is positive half cycle, so the triggering pulse will be given to P1 here. So that's it. So if you understand this concept, the understanding of cyclo converter is pretty easy. Just follow these 4 points, nothing more than that. What are the switches will be in forward blocking mode during positive half cycle? What are the switches will be in forward blocking mode during negative half cycle? And what is the requirement of output voltage polarity based upon your frequency requirement? Alright, so if my output frequency requirement is one half of the supply frequency, two half cycles, the 1 and 2 converted into positive half cycles, 3 and 4 will be converted into negative half cycle, so that my output frequency will be half of the supply frequency. In this way, by giving the suitable triggering pulses to the switches in the cyclo converter, we can obtain those things. And for the better visibility, so these are the textbook waveforms you can go through. These are available in your notes. Now, bridge type cyclo converter with resistive load. So here also just you need to understand. So this is the configuration of your dual converter. So here just identify during, this is the source. So during positive half cycle of Vs, so identify what are the switches will be in forward blocking mode. So P1, P2 from P converter, P1, P2 from P converter. So this is a P converter and this is the N converter. From N converter, so the same plus is applying at this leg. So N1, N2 from N converter will be in forward blocking mode. So observe the configuration. This is similar to your dual converter. So P type converter, a full bridge converter, single phase full bridge converter here, another single phase full bridge converter here. But the direction of the thyristors are reversed. And this is your load. So this is your load. Load is connected here. The same source is connected to P type converter and N type converter. So during positive half cycle of the source voltage, P from the P converter, P1 and P2 will be in forward blocking mode. From N type converter, N converter, N1 and N2 will be in forward blocking. So during negative half cycle of supply voltage, so this becomes negative, this becomes positive, so that P3, P4 from P converter, then N3, N4 from N type converter will be in forward blocking mode. So we know when P1, P2, P3, P4 are in conduction, I can expect positive half cycle in the output. When N1, N2, N3, N4 are in conduction, I can expect negative half cycles in the output. So the output frequency requirement is on load of supply frequency. So during first cycle, that is positive half cycle, so P1, P2 are in forward blocking mode from P type converter, so triggering pulses will be given to P1 and P2, so that current flow starts from A to load to P2 neutral. So positive half cycle expected in the output, and in the second half cycle, that is negative half cycle from the source, but our requirement is positive half cycle in the output, so that the triggering pulses will be given to P3 and P4, because these are the switches are in forward blocking mode from P type converter, and then again P1, P2. So 3 half cycles are completed here, and again for remaining 3 half cycles, N3, N4, N1, N2, again N3, N4 will be given. So here for negative half cycle, N3, N4 will be in forward blocking. So triggering pulses will be given to N3, N4. So this is the basic operation of step down cyclo converter for both midpoint configuration and bridge configuration. Thank you.